The 0s of a polynomial has a multiplicity of n provided factor x minus s appears n times in the factored form of the polynomial. For example, f of x equals x minus 3 squared has only one real zero, 3, with a multiplicity of 2. G of x equals x minus 5 cubed times x minus 7 has two real zeros, 5 with a multiplicity of 3 and 7 with a multiplicity of 1. Consider the function h of x equals x plus 4 cubed times 2x minus 3 squared. Find the zeros of h and determine the multiplicity of each. Here, the zeros are negative 4, which would be this 0. This would add up to 0, and it would make the whole thing 0. And the multiplicity is 3. Here, we have 2x minus 3 equals 0, so 2x equals 3, x equals 3 halves. If you plug 3 halves in here, this becomes 0. The multiplicity is 2. The numbers 1 and 5 are the zeros of f. The factor x minus 1 repeats with a power of 2, and the factor x minus 5 repeats with a power of 2. The graph bounces off the axis at x equals 1, and it bounces off the axis at x equals 5. That's what happens when you have a multiplicity of 2. It just bounces right off. Here, the numbers 1 and 5 are the zeros of f. The factor x minus 1 has a power of 3, and the factor x minus 5 repeats with a power of 2. See how the graph passes through the axis at x equals 1, and it bounces off the axis at x equals 5. Even versus odd multiplicity. For a 0r with an odd multiplicity, the graph passes through the axis at that point, x equals r. For a 0s with an even multiplicity, the graph bounces off the axis at x equals s. Here's a review from algebra. A function is increasing on an interval provided y increases as x increases for all x in the interval. A function is decreasing on an interval provided y decreases as x increases for all x in the interval. Let's now discuss a more technical explanation. Consider a closed interval a,b. Let a be less than or equal to x1, which is less than x2, which is less than or equal to b. If f of x1 is less than f of x2 for all x1 and x2 in the interval ab, then f is increasing on ab. If f of x1 is greater than f of x2 for all x1 and x2 in interval ab, then f is decreasing on ab. Recall that local or relative extrema are the turning points on the graph. Absolute or global extrema are the high and low points on the graph. So here we have an absolute maximum, which is also a local maximum, but there's no absolute minimum. Here we have an absolute minimum, which is the lowest minimum. It's also considered a local minimum. Here we have another local minimum, but because it is higher up than this one, it's not an absolute minimum, it's just local. And here we have a local maximum, which is also a relative maximum. This is the graph of a 6-degree polynomial. True or false? A identifies the absolute maximum. This is true. This is the highest point on the entire graph. B identifies the absolute minimum. No, this is false because there are points to the left and right that are lower than B. So this is a local minimum. A, C, and E are absolute maxima. A is absolute maxima. However, C and E are just local or relative maxima. So this is false. D is a 0 and a local minimum. That is true. Here we have a local minimum, and it's right on the x-axis. This graph has 5 zeros and 6 extrema. There are 1, 2, 3, 4, 5 zeros. However, there are 1, 2, 3, 4, 5 extrema, not 6, so this is false. And there you go. Data of air temperature T versus time, a day in hours, is shown below. Air temperature is a continuous event, so connecting the hourly black dots with a smooth curve makes good sense. The minimum for the day was 58 degrees Fahrenheit, and the maximum was 79.5 degrees Fahrenheit. The temperature range of the day is captured in the inequalities T is greater than or equal to 58 degrees Fahrenheit and less than or equal to 79.5 degrees Fahrenheit, or the same in Celsius. The air temperature on the day is bounded. On the grid, we can see that all of the data is above 55 degrees Fahrenheit and below 80 degrees Fahrenheit. We call 55 degrees Fahrenheit a lower bound and 80 degrees Fahrenheit an upper bound, since the data satisfies this inequality. Determining lower and upper bounds is a bit arbitrary, since 50 degrees Fahrenheit and 85 degrees Fahrenheit are lower and upper bounds as well. Determining lower and upper bounds is arbitrary. With ample data, though, there are ways to define bounds with more precision. To the point, we call 58 degrees Fahrenheit the greatest lower bound and 80 degrees Fahrenheit the least upper bound. The greatest lower bound corresponds to the minimum temperature for the day, and the least upper bound corresponds to the maximum temperature. A function f is bounded below if there is some number c that is less than or equal to every other number in the range of f. The number c is a lower bound of f. A function f is bounded above if there is some number d that is greater than or equal to every other number in the range of f. The number d is an upper bound of f. A function f is bounded if and only if there exist values for c and d, so that f of x is greater than or equal to c and less than or equal to d. A function that does not satisfy the definition of bounded is called an unbounded function. Data of air temperature T versus time, a day in hours, is shown below. Air temperature is a continuous event, so connecting the hourly black dots with a smooth curve makes good sense. The minimum for the day was 58 degrees Fahrenheit at 6 a.m. and the maximum was 79.5 degrees Fahrenheit at 5 p.m. Was there a time between 6 a.m. and 5 p.m. when the temperature was exactly 70 degrees Fahrenheit? It is the intermediate value theorem that assures us that all intermediate values between the high and low temperature are achieved at least once between 6 a.m. and 5 p.m. Of course, the function needs to be continuous to make this claim. If a function f is continuous on the interval a,b, then f will achieve every value between f of a and f of b in the interval a,b. For example, use the intermediate value theorem to demonstrate that the function f of x equals 2 minus 3x to the fourth has a 0 in the interval 0, 1. F of x equals 2 minus 3x to the fourth is a polynomial. Therefore, f is continuous for all real numbers. F of 0 equals 2, and f of 1 equals negative 1. So the intermediate value theorem assures us that f of x will achieve all values between negative 1 and 2 in the interval 0, 1. Since 0 is between negative 1 and 2, there is at least one number k where k is greater than 0 and less than 1, so that f of k equals 0. A number k, f of k equals 0, is a 0 of f.